Good morning. So this is the annual talk for the PhD School of Alex Jimenez Romero that will present only a small part of what he has been doing in this last year. That is a couple of papers of a particular topic.
Okay, so I start. Hello, everybody. My name is Alex Jimenez, and I'm a PhD student here at the FISC. And today I'm going to present my annual talk. It's the first one here at the FISC about a part of one of my research topics, which is modeling parasite-produced marine diseases of immobile hosts that I've been doing with Manuel, which is my supervisor, Manuel Matias. So, well, first of all, I want to introduce you a little bit into the motivation for doing this work, and I will also briefly introduce you into compartmental models, very briefly, because I will be using compartmental models throughout all the work talk. So then I will just explain you the two works that we have done, which is basically a model, a compartmental model for parasite-produced marine diseases of immobile hosts, and we have done two versions, a non-spatial version, and then a stochastic spatial explicit version. And finally, I will comment some further work that we could do in the future. Okay, so regarding the motivation, we have on one hand a biological motivation, which is the mass mortality event of Pinna nobilis. Pinna nobilis is a pen shell endemic from the Mediterranean Sea, and it's also known as giant pen shell or noble pen shell. It can get up to 1.2 meters tall, and you can see an example here in the figure. So this mass mortality event has been caused by a parasite called Haplosporidium pinnae, which is causing a disease to this pen shell. And well, there are several outbreaks in the Mediterranean Sea. Indeed, there is nowadays an epidemic in the Mediterranean Sea, and it is there is a high mortality. So if all the populations of Pinna nobilis in the Mediterranean Sea would die, then the species would get extinguished because it's endemic from the Mediterranean Sea. And well, also we have a theoretical motivation because epidemic modeling in marine ecosystems has been much less studied than in terrestrial ecosystems, where it's well known, and there are a lot of models in the literature. But only recently, some compartmental deterministic models have been developed for marine ecosystems, including the one that I'm going to present. So it's nice to start doing things in marine ecosystems and get some knowledge. Okay, so the brief introduction to compartmental models is only this slide. So basically, in compartmental models, one divides the population under study into different compartments or states, for instance, susceptible, infected, dead, or whatever. And individuals are allowed to move from one compartment to another following some dynamical rules. Okay, so then under an homogeneity or well-mixed assumption, you can write a system of ordinary differential equations. And from this system, you can obtain a lot of results in a relatively easy way. So in epidemic modeling, the typical example would be the SIR model, which is susceptible, infected, removed. So the host population is divided into those states. Susceptible individuals are going to get infected at a given rate beta, and infected individuals will die at a given rate gamma. So then, under this well-mixed assumption, you could write this system of differential equations here, which is quite simple, and you can obtain a lot of results from this system. One of the most important results is the basic reproduction number, which is basically the number of secondary infections produced by a primary infection, which is going to control the threshold behavior of the model. So if this number is above 1, there's going to be an epidemic. If it is below 1, there's no epidemic. We can see this analytically here from the SIR model in a very simple way indeed, just rearranging some terms of this equation. You observe that if these parameters, so this is what defines the basic reproduction number, is greater than 1, the infected population will increase. and otherwise it will decrease, and then there is an epidemic or not. So let's go now to our first work, which is modeling parasite-produced marine diseases, and in particular, the case of the mass mortality event of Pinanobilis. This was done in collaboration with Amalia Grau and Iris Hendricks, and was published in Ecological Modeling last year. So here we are interested in developing a model for marine diseases with immobile hosts. So then we cannot, as the hosts are immobile, they cannot move. So we cannot assume direct contact process between infected individuals and susceptible individuals that, and this would be the process of generating new infections. We need to do another thing. In particular, we need to consider the parasite population, okay? At least at first, at the beginning. So this is something different from most of the compartmental models in terrestrial ecosystems. And then we are going to assume other things. For instance, we are going to assume that there are no births or natural deaths in the system of hosts, because the time scale at which the disease evolves is much faster than the typical life cycle of hosts. And well, with these assumptions, and the homogeneity assumption and so on, we are going to build this system of differential equations. So basically, the processes are the following. Susceptible individuals are going to contact parasites and filter them and getting infected at rate beta, bar beta. Then infected individuals die at rate gamma. Infected individuals also produces parasites at rate lambda, and parasites die at rate mu. Also, when parasites filter, when susceptible individuals filter parasites, those parasites get absorbed, so they are removed from the medium, and is this term here. So joining all these processes, we can write this system of differential equations, where var beta stands for two different ways of modeling transmission, that is standard incidence or mass action, that can take just two forms here or other forms, but these ones have been used in the literature a lot of times. And sometimes this one applies, sometimes this one applies, depends on the condition on the system and so on. And at the beginning, we don't know. So we keep general and we use this symbol to represent both. Okay, so well, we can see that the host population is conserved because we are assuming so, there are no births or natural deaths. And then we have this conserved quantity in the system. Okay, so the first result is the calculation of the basic reproduction number. We can do this in two ways. One way is performing a linear stability analysis of the fixed point, and well, you obtain the result, the pre-pandemic fixed point, which is this one. Then there is other methods, such as the next generation matrix method, that is kind of a generalization of this linear stability analysis, in which you directly compute the basic reproduction number. And well, obviously, both results are the same. And indeed, the formula of the basic reproduction number is quite intuitive, because you have the lambda over gamma would be the mean number of parasites released by an infectious host in its lifetime, and the other term would be related with the probability of a parasite infecting a host. So the next result that we obtained from this system of differential equations was that there is another conserved quantity. Here it is indeed very easy to see it. So from the first differential equation for S, you can isolate P in this way. Then adding up those two differential equations, you can isolate I in this way, and substituting those two equations into the differential equation for P, you obtain this equation. So we can see that all these terms are exact differentials, and then the integration is straightforward, and we obtain the conserved quantity. Now, this conserved quantity can be related to the initial conditions, and in this way you can obtain an equation for the parasite population as function of the states of the hosts, which is this one. And this allows for an exact reduction of this model, which indeed is of three differential equations, because we had already one conserved quantity, to another system with only two differential equations. That is exact. So then another thing that we did, you can see here that we only have two differential equations, but we have the same number of parameters. So maybe it's not that useful. So another thing that we did was a timescale approximation, in which we considered that the death rates of the parasites are much, so the parasites die much faster than infected hosts. And with another condition, which is this one, you can obtain this approximate relation between the parasite population and the number of infected individuals. So basically, the parasite population is proportional to the number of infected individuals. Then with this solution, you can reduce the original system of differential equations to this one, with this that is nothing but the SIR model with an effective transmission rate. Well, obviously, we checked all this numerically. We checked that the previous equation, the exact equation for P, is always working, and it is, and that in this limit, this equation agrees perfectly with the numerical one. Okay, so when you are in this parameter range, you can use the SIR model to describe this system, and this is quite interesting because in the original model we were not considering direct contact between hosts because they are immobile, they cannot move. So in principle, an infected host cannot directly infect a susceptible one. But here you see that in this parameter range, mathematically you can describe this as if there was this direct contact between hosts. And finally, we applied our model to experimental data. We had experimental data of 2 tanks in which P anomalies were kept. The idea was to rescue these individuals and save them in some locations and so on. But well, they were already infected, and then there was an outbreak in each of the tanks. So at least we could have this data to fit our model. First of all, we fit our exact model that depends on 3 parameters. Well, we fixed this parameter, the mortality rate of infected pen shells, because it's known with its uncertainties and so on, but it's known. Well, we optimize the other parameters, and we find that we have a lot of multiple combinations of the parameters that can fit equally well the data. So this value here of optimal solutions. And that is, in order to fit this data, you must fulfill these ratios here. And this ratio is nothing but the effective transmission rate of our reduced model, of the approximate model, the SIR model. So this is kind of telling us that we can fit this data with the SIR model with those values of the beta prime parameter. So we did that. And moreover, we relaxed our assumption of gamma equals 1. So in panel B, we observed that gamma equals 1 is still optimal. So that beta prime is the same number that we had before. But for the other tank, it's a little bit better to consider gamma equals 1.5. And then you can slightly, you can get a slightly better fit to the data, which is this. And well, this is all for the first part. We can conclude that we have developed a non-spatial compartmental model for parasite-produced marine diseases. We have found an exact solution for the parasite population as function of the host state, which allows for an exact reduction of the model. We show that if parasites die faster than infected hosts, an SIR model is able to describe this system. And the model has been confronted with experimental data, being able to fit this data, and indeed showing that the SIR model, which is the simpler one, is able to fit the data. And this suggests that, at least in the experimental setup, the parasites were dying faster than the hosts. Now, let's go to the second model, in which we basically add space and stochasticity to the previous one. This model, or this work, was done with Federico Vázquez and Cristóbal López, and has been recently accepted in Royal Society Open Science. So, as I have said, the model is basically the same, the processes are the same, but now we have space, which is a square lattice. In each cell, we place a host. This is a scheme, but in the real model, each cell has a host. And parasites are allowed to move through the lattice following a random walk, so random. So all the processes are the same, but we have one more process, which is the the parasite mobility with its parasite mobility rate kappa. So now we have one more parameter. So here I want to show you an example of the dynamics of the model. So here you can see how the parasites are moving through the system. The pen shells are getting infected, they produce parasites, and so on, they die. And you can see here how the total population evolves of parasites, and these are the states of the hosts. This is one realization of the process. It is stochastic, so each one would be slightly different. And now let's go to the results. So first of all, we check the non-spatial limit that should coincide with the system of differential equations that we had before, because it was the non-spatial model. So in this case, the non-spatial limit is reached when parasites can interact with any host in the system. So before dying or disappearing in any way. This involves a high mobility regime. So basically, if kappa is greater than mu and beta, this means that the parasites will move many times before dying with mu or getting absorbed by a pen shell. And then parasites infect a random host of the system with this probability, and you can then write this system of differential equations. So we check this numerically, and when you are in this limit of very high mobility, you see that the stochastic model, the spatial model, and the system of differential equations have the same solution. And also you could use the analytical expressions that you can find with this system of differential equations in this model, because they are the same. Okay, then another thing that we wanted to see is if the approximation for P as function of the number of infected individuals, so this one that we derived before, still applies in the spatial system. Of course, if you are in the high mobility regime, in which you are in the non-spatial limit, you have the same that we have before. That would be panel A and B. So you need to be with mu greater than gamma and beta, as I showed you before, so that the approximation is valid. If not, it doesn't work. But we observed that in the low mobility regime, independently on this condition, the approximation is still valid, but you need another one, which is this one. And we can explain this. So basically, if you are in the low mobility regime, so if kappa is smaller than lambda and mu, lambda is the production rate of infected host, and mu is the death rate of parasites, then in those sites in which you have infected individuals, the only things that can happen is production and death of parasites. Okay, and they could also move, but it is not very probable in comparison with the other ones. So, and they cannot infect the pen shell because it's already infected. Okay, then you can write let's say that those cells would be like a closed system, and you can compute the evolution of the parasite population in this cell, which is like a closed system. You can see that you have an equilibrium value, which is this one, and it could be reached in a time proportional to 1 over mu. Then as kappa is smaller than mu, then the typical time that a parasite needs to move, that is 1 over kappa, is greater than the typical time in which you reach equilibrium. And so all the cells would be at equilibrium, and you can compute the total number of parasites in the system approximately as the number of cells with infected individuals times the equilibrium value of parasites in each of those cells, which is again our approximation that we had before. And well, we see that it is working in these limits. Okay, then we computed an approximation for the spatial basic reproduction number. So in this kind of models that are spatially explicit and stochastic, it is quite difficult to compute an exact formula for the basic reproduction number. But we managed to give an approximation that works quite well. So in this case, we can understand this as that we can compute the number of secondary parasites that are able to produce new infections, or it's the same to compute the number of secondary infections produced by a first infection. But in this way, I think it's easier. So you just imagine that you have one parasite in a fully susceptible population. So the probability that this parasite will infect a host is this one here, independent of mobility, because if it moves or not, he's always in a cell with a susceptible host. Then this infected host will produce a parasite with this probability, or will produce this, in average, this number of parasites or whatever. And then these parasites will move to neighboring sites with this probability, because they cannot infect this. So the potential in this site, because it's already infected, so they can or die or move. And well, joining these terms, multiplying these terms, you obtain this expression, which is nothing but the non-spatial basic reproduction number multiplied by a mobility factor. And indeed, we observe that if we take the limit of high mobility in the high mobility regime, so the non-spatial limit, this would be 1, and then the basic reproduction number of the spatial model in the non-spatial limit would be the non-spatial basic reproduction number, which it makes sense. Okay, so well, we also see that if we have lower mobility than in the non-spatial limit, the critical value of this basic reproduction number must be greater than 1, while in the non-spatial limit is 1. Okay, so we need to be more infectious if the parasites move less, which is reasonable. Well, then we expect the transition from no outbreak to outbreak to occur at the value for the spatial basic reproduction number equal 1. So then you can relate the critical value of R0 to the mobility factor in this way. And we check if this is working or not. So we numerically computed the phase diagram that you can see here. And we fit this formula. So we allow for a more general expression of this formula, and we check that B is -1. But obviously, we have some correction factors here. If our formula was perfect, A would be 1 and C would be 0, but it is not because it's an approximation. So we have some corrections here. But at least the dependence with the mobility is well captured. So, well, we see that here, when we are approaching the non-spatial limit, the critical value for the basic reproduction number is 1, as it should be. And all these things that if you have low mobility, you need very high values for the non-spatial basic reproduction number. So you must be very infectious in order to produce an outbreak and so on. And another thing that we observe is that if you are near the critical point, host-to-host transmission occurs only through nearest neighbors, while if you are above the critical point, you have long-range transmission. So in this, we can see this here in this row, we are near the critical point. In the second row, we are above the critical point, and those blue lines are cells in which there is no host. So there is only water. Parasites can move. There is any barrier or whatever. But what happens is that they cannot infect anyone there in those cells because there is any host. There is any host. So we observe that here the disease is only in this patch. It remains in this patch, while here it would spread to all the system. While if you are above the critical point, these gaps are not enough to stop the epidemic. If we put wider gaps, it would be, because this long-range transmission will be up to some length. But here we can see this difference. No? Okay. Well, another thing that we computed, 2 things more and I'm done, is the spreading speed of the infected population. We have seen how the infected population spreads. So the disease spreads, not the individuals because they cannot move, but the disease. And well, we observed that, well, we showed that the spreading speed of the infected population is proportional to the square root of the mobility rate of the parasites. Indeed, this is expected because by analogy with diffusion. And this is more interesting because the spreading speed of the infected population also increases with the square root of the distance to the critical point. So you can have the same mobilities. For the same mobility, if you increase the distance to the threshold, the infected population spreads faster. But the mobility of the parasites, which are the agents that produce the disease, is the same. Okay, and Finally, we computed the time to extinction, which is the time elapsed from the beginning of the epidemic until the system reaches the absorbing state, which in this case is that there are no parasites and no infected individuals left, so the dynamics stop. Well, we expect that the time to extinction increases when kappa decreases because of the spreading velocity that we have seen. And we also expect that the time to extinction decreases when the distance to the threshold increases, also because of the velocity. So this is what we see in the slide before. And this is observed, obviously. We also observe that extinction peaks. So the values of the non-spatial basis reproduction number at which the extinction time peaks corresponds to the critical values of the basic reproduction number. And this allows to collapse these curves. And the last, let's say, formula that we derived is the following thing. So if you are far from the critical point, so if your basic reproduction number is high, you will reach the absorbing state because all individuals will get infected and then they will die. So in this case, the time to extinction should be inversely proportional to V, to the spreading velocity. And then you obtain this formula, and it works pretty well in this regime. So, okay, these are all the results for the spatial model. So, to conclude, we have said that we have developed a spatial stochastic model for marine-produced diseases of immobile hosts. We show that in the adequate parameter range, we recovered the non-spatial limit, as it should be indeed. We extended the approximation for the parasite population as function of the infected individuals for the spatial case with low mobility regimes. We derived an approximate expression for the spatial basic reproduction number that works pretty well. And well, we studied the spreading speed of the infected population and the time to extinction, and derived some analytical expressions for these quantities also. So, brief comment on what could we do in the future. We could, for instance, allow that infected individuals can still filter parasites. That it's not included in the model, but it could be relevant indeed. We could also introduce parasite load dependent processes or more things. So basically, we could build modified versions of this model, including different processes. And also, we could build a metapopulation model in which parasites would spread by surface currents. Indeed, this is the way they are traveling long distances in the Mediterranean Sea. They know that. So we could build this kind of model and try to feed maybe some data and so on. But I'm not sure if there is data. I'm not sure if there is much interest on these topics now. So I don't know. And well, these are the references. And thank you for your attention. If you have any questions.
Thank you, Alex. The paper or the papers are open for discussion.
Hello. Nice work or works. Just two questions. One is I become lost in your slide 14 on the long range and short range. I don't understand what.
Okay. This one, no?
Yeah, this one.
So, okay, here we have to compare those two, and those two. Okay. So basically, in these two plots, we have the same basic reproduction number here in those plots, and it's near the critical point. So the spatial basic reproduction number would be, I don't know, 1.2 or something like that. So here we observe that there is an outbreak, and indeed it's like quite large. It's spreading to all the system. And here what
what is in the green region?
So
the green region
each pixel, if the pixel is green, is a host, a susceptible host. If the pixel is red, is an infected host. If the pixel is black, is a dead host. And here, if the pixel is blue, is that there is nothing there. Well, there is water. So the parasites can move and so on, but they cannot infect anyone there. So then the transmission stops if you are near the critical point. But if you are above the critical point, you have this kind of long-range transmission. So parasites move and can infect someone that is 2 or 3 or 4 cells far away, let's say. So for this reason, they can cross here. This is, but obviously, maybe for this value of the basic reproduction number, the long-range transmission is 5 cells. I don't know. So, and this is 2 cells. See, if you did this wider, you could also stop the epidemic. So, indeed, it would be interesting to compute this. How long is the transmission depending on this spatial basic reproduction number or whatever? But we didn't do it analytically. Indeed, we didn't remember until I saw these videos the other day, and I remember that it was very interesting. But the paper also was long, so. But yeah, I would like to do it.
And now, just a remark: when you say that in the parameter in which you put the mortality of the parasite, I think this mortality, but this can also model the part of the parasites that leave the region of interest.
Yeah.
See. That is interesting
be,
to.
Yeah.
It's a factor that you are in fact taking into account, but you don't take track of it. And just, of course, it would be nice to consider all the currents, but I think that the simplest improvement and the simplest consideration of current is just to put a one directional current on top of the population and see
what happens. Yeah.
This would be the simplest thing to do.
See, yeah.
Okay. Thank you, Alex, for the talk. It was very nice. I have a question. Maybe it's a little bit naive. It's about when you did the fit of the model with the experimental data.
This one? No.
No, the first one. I mean,
this or this?
That one. Just that you find a ratio of 2 parameters that give you the good approximation.
See, well, I find that all the parameters that fulfill this ratio fit. So, for instance, those 3 have the same ratio, but they are different, but have the same ratio, and the curve is the same.
Okay. This problem is because your model do not find difference when you put that values. I mean, the results are the same.
No. So the thing is that this curve is the same, but not all the curves of the model.
It's just you don't have the data of the curve that
Claro.
different.
Exactly. Maybe in one you have like the parasite population, like this curve would be like the same, but if you plot the parasite population with one of those parameters, maybe it's like this, and with the other is like this, or so you have differences in the other. For instance, in models of vector-borne diseases, it also happens this kind of things. That maybe indeed the basic reproduction number is the same if you change the infectivity of plant to vectors and vector to plants. So I don't know if you have alpha and beta, you can interchange the values. So, and the final number of dead individuals for the host is the same, but how the populations of infected vectors evolves is different. But the final result for the hosts is the same. And here we only have this curve. So yeah, you have not enough data to know which of these combinations is the good one. That's so for this reason it's happening.
Okay, I have another question. I don't know if somebody something. It's a little bit related with this. I don't understand very well when you present the equations. These parasites, the P, is the number of parasites or is
the P?
See, yeah, for me it's weird that the 2 betas, or the betas, that how many parasites are absorbed and how many individuals are getting
infected. You could have another term, like an efficiency term of.
Yeah, so it is scales, no? How the population.
Yeah, but for us it's 1.
And when you consider that the parasites are moving, I mean, you now one parasite in this model will be, for example, 1,000 parasites, no? But when they are moving randomly, you just consider one of them moving randomly. So I don't understand.
All are moving random. In this one, well, you start with you don't start with 1 because always it's very probable that he dies. Or you start with a little, I don't know, 50 or whatever, and then they are moving. but all are moving.
Okay.
Sí. I don't know if this was the question.
I don't know very well how to formulate it, but yeah, more or less. I have a question regarding this spatial model. You always assume that the underlying structure is a square lattice,
Yeah.
right?
Yeah.
And my question is that realistic? Do you know how they are?
Yes.
In the
Yeah.
Mediterranean
Bueno,
cities?
now they are not because they are all dead. But yeah, they were. So there used to be a huge. Well, in some places huge, in others not that huge extensions in which you had not a perfect lattice, obviously, but you had like. For instance, I know that the density was quite low. I think it was 1/100 square meters, and you can see pictures in where there is I don't know how to say it, but a lot of pen shells more or less like this. But if you go to, it depends on the scale, because if you have a bigger range, then you would observe one population here, another population in another place, another population in another place. And this is why the next model could be this kind of meta-population model. So the idea would be that each of the populations could be connected, that the parasites could travel from one to another using the currents or whatever.
Okay.
But yeah, for one population, the structure is like this, more random, but it's not like a network.
But could it be, for example, a more realistic assumption and a geometric random graph? So you just put points randomly and connect them.
Yeah, maybe. But the thing is that maybe it's more difficult to implement the spatial modeling, but because the distances wouldn't be the same. I don't know. But I don't think it's very, very important.
Okay.
But yeah, it could be checked.
Thank you.
Well, I would like to go back to 14, to slide 14 as I mean, I think as the way you presented, you seem to imply that there is a threshold somehow. I don't think that's the case. No? So I mean, in the first case, if you wait long enough, you will probably eventually will jump to the other one and will spread. So it's just a matter that you are lowering the probability, no? So
No, they can jump. Indeed, there is one.
Then one jumping there.
Yeah.
And then,
but it's not
it
enough.
dies.
It's not enough to continue the.
No, but you wait long enough, it will at a certain point. It's just you are lowering the probability of crossing.
Bueno. Yeah.
That is
Vale.
legit.
Yeah. Sí. Well, but it's very, very small. Yeah. Sure, but. Sí.
More questions? We are in family. Miguel, you don't want to ask? Okay. Thank you very much. Thank you, Alex. If there's anyone in the audience who wishes to ask any question, she can use the chat, I guess. Okay. Or you can just unmute. Yes, thank you, Miguel. You can just unmute and ask. It's better, yeah, because there are only 4 people. No? Okay. Thank you, Alex.
Leo.
Bien, Alex.
Che era la color bar? La color bar dall'animazione italiana. Quella sezione. Questa color bar.
deixo com a punts